Hello, and welcome back for the last lesson of chapter 4. We're still working with discrete data, but now we're going to talk about the binomial distribution. The binomial distribution is a specific situation with discrete data. Bi is a prefix for 2, like a bicycle. And so what that means is there are 2 outcomes. So there's 4 characteristics that tell you if your experiment satisfies a binomial experiment. And I will be asking you to qualify all 4 of these in some questions throughout the semester. So there are a fixed number of trials. Think of trials as repetitions of an experiment. The letter N denotes the number of trials. So we have to have a fixed number of trials. There are only 2 possible outcomes, success and failure, for each trial. The letter P denotes the probability of success on one trial, and Q denotes the probability of a failure on one trial. And because you can only have success or failure, the 2 of them added together, P plus Q equals 1. Define X as the number of successes. And X, you can only have either 0 successes all the way through N successes, the number of trials. And the 4th characteristic is that N trials are independent and are repeated using identical conditions. Because the N trials are independent, the outcome of one trial does not help in predicting the outcome of another trial. Another way of saying this is that for each individual trial, the probability of P of a success and a probability of Q of a failure remain the same. So they're independent, the probability stays the same. So if you were doing an example where you were drawing cards and you were not replacing the card back in, that could not be a binomial distribution experiment because you did not replace them and the probability is changing. So it's just look, it says, for example, randomly guessing at a true-false statistics question has only 2 outcomes. If a success is guessing correctly, then a failure is guessing incorrectly. Suppose Joe always guesses correctly on any statistics true-false question with probability that he guesses right is 0.6, then the probability of him guessing incorrectly is 0.4. This means that for every true-false statistics question, Joe answers, his probability of success 0.6 and his probability of failure 0.4 remain the same. The outcomes of a binomial experiment fit a binomial probability distribution. The random variable X equal to the number of successes obtained in the N independent trials. We can calculate the mean of these experiments by multiplying N, the number of trials, times the probability of success. And the standard deviation of these trials is calculated by the square root of N times P times Q, where N is the number of trials, P is the probability of success, and Q is the probability of failure. And Q is the same as 1 minus P. So this could also be written as this, N times P times 1 minus P. Any experiment that has characteristics 2 and 3, where N equals 1, is called a Bernoulli trial, named after Jacob Bernoulli, who in the late 1600s studied them extensively. Okay, so let's just jump into some examples. At ABC College, the withdrawal rate from an elementary physics course is 30% for any given term. This implies that for any given term, 70% of the students stay in the class for the entire term. A success could be defined as an individual who withdrew. The random variable X equals the number of students who withdraw from the randomly selected elementary physics class. Okay. So we define what a success is, and we defined how we're calculating X, the definition of what we're counting successes. Let's look at we're going to try one. It says the State Health Board is concerned about the amount of fruit available in school lunches. 48% of schools in the state offer fruit in their lunches every day. This implies that 52% do not. And that's because 100% minus 48 equals 52. They must add to 100. What would a success be in this case? So X would be the number of schools that offer fruit in their lunches. That's what we're counting. Example 2, it says, suppose you play a game that you can only either win or lose. The probability that you win any game is 55%, and the probability that you lose is 45. They add to 100%. Each game you play is independent. If you play the game 20 times, write the function that describes the probability that you win 15 of the 20 times. Here, if you define x as the number of wins, then x takes on 0 to 20. The probability of success is p equals 0.55. The probability of a failure is 0.45. The number of trials is n equals 20. The probability question can be stated mathematically as this. We want to know exactly 15 times. That's what their question was. So let's practice writing that. A trainer is teaching a dolphin to do tricks. The probability that the dolphin successfully performs a trick is 35%, and the probability that the dolphin does not successfully perform the trick is 65. Out of 20 attempts, you want to find the probability that the dolphin succeeds 12 times. State the probability question mathematically. So we are doing the probability that x equals 12, because we want to know what's the probability he succeeds 12 times. We're going to learn how to find these probabilities, the actual answer here in a minute. Next example. A fair coin is flipped 15 times. Each flip is independent. What is the probability of getting more than 10 heads? Let x equal the number of heads in 15 flips of the fair coin. X takes on the values of 0 to 15. Since the coin is fair, probability of success is 0.5 and probability of failure is also 0.5. The number of trials is n equals 15. State the probability question mathematically. So it said, what is the probability of getting more than 10 heads? So greater than is more than. So it's a strictly greater than. In your, just a reminder, in your formula packet that I've given you, your exam notes packet, it's going to say page 298. This gives you the 4 requirements for a binomial experiment and also the wording that you're going to use. Now, this function here is only if you're using a TI-84 calculator. I give you plenty of instructions during the notes using Desmos, which I would recommend using Desmos because that's what we're using pretty much for the whole semester. But if you have a TI-84, you can use these, and I give a little scenario of that as well. Okay, but what's important are the phrases and the symbols that go with that. So we said greater than or more than, and so that's a greater than with no equal to. It's a strictly greater than. For example, 3. So let's look at the you try it. A fair 6-sided die is rolled 10 times. Each roll is independent. You want to find the probability of rolling a 1 more than 3 times. State the probability question mathematically. So we want to find the probability that x is greater than 3. Our outcome is rolling a 1, but we want to find the probability of getting that 1 more than 3 times. We're going to start putting these all together, the whole big picture. Example 4 says, approximately 70% of students do their work in time for it to be collected and graded. Each student does homework independently. In a statistics class of 50 students, what is the probability that at least 40 will do their homework on time? At least 40 is important. Students are selected randomly. This is a binomial problem because there is only a success or a failure. There are a fixed number of trials and the probability of a success is 0.7 for each trial. So So B, if we are interested in the number of students who do their homework on time, then how do we define X? X is equal to the number of statistics students who do their homework on time. What values does X take on? 0 through 50. You could have 0 of them that turn it in on time or all 50 of them. What is a failure in words? Failure is defined as a student who does not complete his or her homework on time. The probability of a success is 0.7. The number of trials is n equals 50. And then we know that P plus Q must equal 1. So what is Q? Q is equal to 0.3 because 1 minus P is Q, and that's 1 minus 0.7, which is 0.3. Remember, they're complements, meaning they add to 1. And the last question says, the words at least translate as to what kind of inequality for the probability question. And that is right here, greater than or equal to. And again, the words at least go with the symbol right here, number 5, greater than or equal to, at least, or not less than. I'll use that symbol right there. The left is greater than or equal to the right. I'd like you to look through the You Try It number 4 and see if you can answer this on your own. I'll be right back. Okay, so let's look at You Try It number 4 together. 65% of people pass the state driver's exam on the first try. A group of 50 individuals who have taken the driver's exam is randomly selected. Give 2 reasons why this is a binomial problem. Okay, so 1, we have a fixed number of trials, n equals 50. Outcomes are independent. 1 driver to the next. So 1 driver passing the exam shouldn't affect the other drivers. And another one would be only 2 outcomes, pass or fail, and the probability of success is 0.65, and that means Q is 1 minus 0.65 or 0.35. The probability of failure. So the second part of this video, there's going to be 2 parts to this lesson because it's a little bit longer, is going to go over building this probability distribution function and how it's notated. So I'm going to give you the notation and we're going to catch me in the next video. The notation for the binomial function is like this, and this is read as a tilde. This symbol here is a tilde symbol. It means kind of like approximately or can be described as. So X can be described as, B is going to tell you that it's binomial. And then N comma P means that the Desmos knows, or the reader knows, that you've had N trials and the probability of success is. And you only need those 2 things to help you find the probabilities. And we're going to learn how to do that in the second part of the video with a bunch of examples. So catch me back for the second video for lesson 4.3.